Hi everyone, this is Andrew here, and today I'm going to be giving my video presentation for MAD3107 Discrete Structures with Professor Maky Manchola. So today my video presentation is on the proof of the combinations formula, or as many people know it, also known as the Pascal's triangles formula. Let's go ahead and start with our proof. Now I want to start by introducing our problem statement. So our problem statement says that we want to let n and k be integers such that n is greater than k and k is greater than or equal to 0. Now we want to prove that n combination k plus n combination k plus 1 is equal to n plus 1 combination k plus 1. And we want to start off our proof by designating that let n and k be in the set of integers such that n is greater than k is greater than or equal to 0. We want to prove that n combination k plus n combination k plus 1 is equal to n plus 1 combination k plus 1. So essentially that the sum of these two expressions right over here on the left-hand side is equal to our right-hand side. To prove this, we want to compute both the left-hand side and right-hand side by doing some simplification, a little bit of algebra magic, and compare them both to be equal so we can establish the goal in our proof. Now let's calculate the left-hand side first. Now we know from the expanded version of n combination k that it's equal to n factorial over k factorial times n minus k factorial. When we do the proper substitution for our little fellow n combination k plus 1, we want to say that the expanded version is n factorial over k plus 1 factorial times n minus k minus 1 factorial. Given that, we bring these together as a sum and we end up with n factorial over k factorial times n minus k factorial plus n factorial over k plus 1 factorial times n minus k minus 1 factorial. Now, what we notice is these two expressions do not have a common denominator, and we need to find a common denominator in order to add them successfully. So how do we do that? Well, what we can do is that we can take each single expression, break it off, and multiply it by the corresponding denominator of the opposite expression. So for example, for our n combination k expression, we can multiply that by the denominator of the n combination k plus 1 expression. And for the n combination k plus 1 expression, we can multiply it by the corresponding denominator of our n combination k expression. Once we do so, guys, we arrive at a long and expanded expression with a common denominator, and it's n factorial times k plus 1 factorial times n minus k minus 1 factorial plus n factorial times k factorial times n minus k factorial over k factorial times n minus k factorial times k plus 1 factorial times n minus k minus 1 factorial. So what can we do here? So we notice that we had two n factorials in our numerator. So we can factor out the n factorial. So factoring out the n factorial, we now open bracket here, and we are left with an inside bracket expression of k plus 1 factorial times n minus k minus 1 factorial plus k factorial times n minus k factorial. And in your expression, in our denominator, we are left with the same common denominator that we found in our expression. Now, for basic factorial knowledge, going back and forth, a little refresher, we know that k plus 1 factorial is equal to k plus 1 times k factorial. So we can replace that in our numerator as well. Once we do so, let me go ahead and show it in our first page of left-hand side continued. We are left with n factorial times k plus 1 times k factorial, which was the proper substitution that we made for the k plus 1 factorial, times n minus k minus 1 factorial plus k factorial times n minus k factorial over our common denominator that we found in the original steps when we multiplied. Now, very simple. When we go to our next step, we notice that the same way that we had two n factorials in the numerator, we had a k factorial as well, two of them in the numerator. So the same thing that we did to our n factorial, we could do to our k factorial, which is just basically factoring that out. Now, noticing that we factored out that k factorial, we have a k factorial in our numerator, and we also have a k factorial in our denominator. So if we take our little trusty handy little pen over here, and we get this fellow, we can say, all right, so we have this k factorial, we got this k factorial, these should basically cancel out. Very simple, no problem indeed. And when we go back to show, we notice our expression is simplified to n factorial times k plus 1 times n minus k minus 1 factorial plus n minus k factorial. And our denominator is simplified a little bit since the k factorial disappeared, and we're left with n minus k factorial, k plus 1 factorial times n minus k minus 1 factorial in our denominator. Now, we know that n minus k factorial is just equal to n minus k times n minus k minus 1 factorial. So the same thing we did to our previous step, we can also replace that in our numerator. So now we're left with n factorial times k plus 1 times n minus k minus 1 factorial, plus this time we have an n minus k times an n minus k minus 1 factorial because we made that substitution right over here. And we're left with the same common denominator from the first step over here. Knowing that we have two n minus k minus 1 factorials in the numerator, we could just factor those out. And we're just essentially left with n factorial times n minus k minus 1 factorial. And then in the brackets, we're left with k plus 1 plus n minus k, as we can see. Now, very simple. Since we have our n minus k minus 1 here, and we have another n minus k minus 1 here, the same thing that we did to our k factorial, this little guy can disappear. So this fellow disappears, and this fellow disappears. Sayonara, baby, they are gone. So going back over here, we're left with a more simplified expression of n factorial times k plus 1 plus n minus k over n minus k factorial times k plus 1 factorial, as this is our new simplified denominator. Now, that k plus 1 plus the n minus k inside the numerator, inside the bracket, those can be combined. So we're left with n factorial times k plus 1 plus n minus k in brackets over the n minus k factorial times the k plus 1 factorial. Now, very similar as we did our cancellations. Very, very similar. These k's right here cancel out just because there's a positive k and there's a negative k. So once we do that, we end up right here with an n factorial times n plus 1 because we're left with that 1 plus n that was right here in the numerator over the n minus k factorial times the k plus 1 factorial that we had in our denominator. So those k's just basically canceled out. Nothing new, nothing bad. Now let's make one little last note before we conclude our left-hand side, that n factorial times n plus 1 is just equal to n plus 1 factorial. So once we do that, we'll end up with a simplified expression of n plus 1 factorial over n minus k factorial times k plus 1 factorial. We can't do much with this. So what do? We can say right now that this concludes the calculation of our left-hand side of the formula. Now let's look at the right-hand side. Let's calculate the right-hand side. Looking at n plus 1 combination k plus 1, when we make the proper substitutions, we know that that's just equal to n plus 1 factorial over k plus 1 factorial times n plus 1 minus k plus 1. Like I said, those things in the brackets, they can combine together with no problem whatsoever. So knowing that they can combine, we notice that we have a positive 1 in the denominator inside those brackets, and when we have a negative 1. So meaning when we take that little pen, that positive 1 and that negative 1, they just cancel out. So once we do so, and go back to our little cursor right over here, we're left with a simple expression of n plus 1 factorial over n minus k factorial times k plus 1. But what did we notice? Well, we obviously noticed that if we go back to our left-hand side continue page, this expression right over here, n plus 1 factorial over n minus k factorial times k plus 1 factorial, is just very similar to the one over here, which was just n plus 1 factorial over n minus k factorial times the k plus 1 factorial. So, therefore, well, what can we conclude? We can conclude that since our left-hand side is equal to our right-hand side, therefore, hence, our n combination k plus n combination k plus 1 is equal to n plus 1 combination k plus 1. Now, I want to thank you guys for watching so much. And we have, as said, we've completed our proof, and we've proven that the left-hand side is equal to the right-hand side. So thank you guys so much for watching.